All right, hello everybody. Thanks for coming. Um, my name is Jeremy Powell. And I work for AMD. And I'm here to introduce to you quickly our new feature called AMD Trusted I/O. So as a back history of where we were, and we spoke about this today a little bit, we've had two beginning states of our feature, which are secure encrypted virtualization and encrypted state. These two provide the confidentiality features of our confidential compute solution, and they are present in EPYC, first generation and second generation. Now, coming to our third generation, we introduced secure nested paging. Secure nested paging is the point where we introduce the integrity and confidentiality, and with that, we've been able to talk about having the hypervisor being drawn out of the trust boundary of a guest. So now we have the question of what do we do with I/O devices. At this point in an EPYC third generation, devices are outside of the trust boundary of a guest. Now we're trying to bring that into it. So SNP's goals were to draw the hypervisor out of the trust boundary. We do this by through a data structure in memory called the RMP. The RMP provides a per 4K granular page set of security attributes for each page, and it's deeply rooted in our address translation features. So both the IOMMU and the CPU MMU are using this RMP data structure to say whether or not a page is assigned to a guest or a page can be accessed by the hypervisor. Another major portion of SNP is our AMD Secure Processor, the ASP. You may have heard it called the PSP. It's the same thing. The ASP is involved in the general orchestration of lifecycle of an SNP guest, and it provides a secure interface to the guests as well as to the hypervisor for control. And so we have some upstream support for guest kernels, and we're working on the host side. So here's the state of things today. When a guest wants to interact with an untrusted device, the untrusted device can DMA into shared memory. When the untrusted device touches shared memory, the IOMMU treats it as if it's hypervisor access. And so that way we can have safe but usable access to devices. However, the RMP will check to make sure that that when the device accesses it, it's not accessing private memory. Same thing goes for the MMIO. Whenever a guest accesses MMIO, it has to be done through a shared memory address. If the guest were to try to p-validate, which means to accept an MMIO range into its private address space, that would be rejected. That's not a possible thing in current SNP guests. So one of the downsides of drawing devices out of the trust boundary of a guest is you have to bounce buffer. So instead of having a untrusted device talk directly to private memory, we have to bring the untrusted device's DMA into a bounce buffer, and then the guest has to burn its own CPU cycles to copy that memory from shared memory to private memory. So when we introduced Trusted I/O for SEV, we have to say, okay, well, we're going to relax the security policy to some degree to allow a device to touch private memory. But we need to provide control to allow the guest to say, I trust this device. So and at the big picture, the untrusted device hands a attestation blob or blobs to the guest, and the guest examines that as part of its attestation flow. And then it says, I trust this device. and it tells the AMD security processor, which does a bunch of SoC magic, to say, okay, this is a trusted device, and it can now touch guest private memory. So now we have MMIO. The guest can now, through our TIO interfaces, allow for MMIO to be mapped into private memory, and the RMP will allow that. Similarly, the IOMMU will allow DMA to private memory as long as the ASP has provided, has marked that device as trusted for that particular guest. So kind of stepping down one level into the architecture, we have a bunch of setup and pieces and parts that bring this all together. There is a control channel between the ASP and the SoC and our devices, our trusted endpoints, called SPDM. SPDM provides a means in which to send specific messages to the device to ask it to enter certain secure states and to set up the next point here, IDE, which is integrity and data encryption. So IDE is it can be a link level, or it can be a point-to-point. What we're talking about here is point-to-point, and it's going to encrypt all traffic, encrypt and authenticate all traffic from the IDE controller in our root complex all the way to the port of the trusted endpoint. The AMD security processor has to go through a few steps on behalf of the guest to ensure that not only the page mapping that we have, page mapping protections that we have for SNP in general for DRAM pages, where the hypervisor is not allowed to do page swapping attacks. We also want to make sure that the MMIO ranges are the actual device that the guest expects, and we're talking to the offset in those ranges that the guest expects. So the AMD security processor will do some work on behalf of the guest to determine that, and then it will tell the RMP, it'll write it into the page of that MMIO offset, that this MMIO range is accepted, and it'll provide, it'll unlock that MMIO range for the guest. A new thing we've added to the architecture is this concept, the data structure called a secure device table. If you're familiar with our IOMMU architecture today, we have a device table. This is in addition to the device table. It's a secure device table that contains the per device security attributes associated with the guest. So today, the device table contains things like guest paging mode. We've moved that out into our secure device table, and now this is where the IOMMU will look to find information about how to tag the accesses of DMA from the device to the guest's private memory. Excuse me. The ASP also has to program this because the SDT is inaccessible to the hypervisor or the guest. And the ASP will retrieve information about paging modes or other things that the guest provides, the guest needs to provide, like where the page tables are, in order to put it in there for the guest. And so then the IOMMU will tag those accesses appropriately. So now this SDT represents sort of a, rather than always considering it hypervisor access, now it can access it as if it's a guest. So in order for this all to work, we have to work closely with the devices. Devices need to provide some isolation between guest workloads. They need to provide a way to freeze and attest to the state of the device. And so we have this PCI standard that was ratified last year called TDISP. And TDISP will places the requirements of having a state machine for each TDI. TDIs are the PCI parlance for an assignable interface that have these requirements. places a state machine that controls the configuration of the interface. It places the requirement for IDE, and it has a whole bunch of transaction level rules that control how packets flow on that PCI fabric. Also, through the requirement of SPDM, they have brought in concepts of authentication and attestation through SPDM channel. And the mapping between AMD's technology and the spec is the TSM and the TDISP spec is the ASP, and the TVM is the SNP guest. The state machine basically provides a way to tell the device to stop letting configuration that might change the security configuration of a device until the guest has allowed, or excuse me, until the guest has attested to that or retrieved the attestation information of that device. So we don't want the configuration to change after the guest is asked for the configuration and has accepted it. The locked state and the run state are the security states. The unlocked state is legacy behavior. So when a guest does attestation, it will ask the ASP to transition the device or the interface to the lock state, and then it will ask, hey, give me all your attestation information. The guest will accept it, and then the TDI will be transitioned to the run state, and that's when DMA and IMMIO can happen. In some cases, the device could choose that, could say, I've reached an error that is insecure, and I need to nuke all the guest data inside of me. So it can transition its interface to the error state, and it can basically sit there until it's purged all of that guest private data. So the guest TDI lifecycle is kind of married together. We're really talking about how do we bind TDIs to guests. First, the hypervisor will want to set up that device connection. It will ask the ASP to set the device connection up and build that SPDM channel, build the IDE channel between the hardware and the device. And then it will do TDI operations to bind the device or the device's interface to the guest. So this is where we say in this SoC, we program the SDT. We say this device interface is bound specifically to a guest, and we don't allow TDI to be bound to multiple guests at a time, so we're enforcing that invariant. Once the TDI is bound, the guest will retrieve the attestation reports and go through that validation flow, and then it will ask the ASP, hey, now that I understand what this device is configured, I want you to program the RMP and allow that private memory MMIO access. And then following that, it'll unlock DMA by programming the IMU, the STTE. There are a number of open questions, I think, in this flow. The question of whether or not devices should be enumerated as TDIs, already locked and run, or if the guest should be able to access, or sorry, request that the TDI is bound to that guest actively. I think a lot of that has to do with the specific guest and hypervisor architectures. So one of the things that we'd like to talk about today in the BOF is, or one of the BOFs is to discuss how this all merges together. Taking one further step down, we have a number of firmware commands that help this process through. We have some commands to manage the device's lifecycle. We have some commands that manage the TDI lifecycle. And we have some commands or guest messages that allow the guest to operate on the device from within the guest. So if you're familiar with SNP, we have a thing called a guest context page. This is a buffer in memory that the hypervisor donates to the ASP, and the ASP stores a bunch of context information about that guest for the purposes of S&P. So in this way, we have kind of extended that concept to devices and TDIs. So we'll have a context page for a device that'll contain a bunch of stuff like the SPDM state, and then we'll have a TDI context that will describe the information about what we expect the state of the TDI to be. So this is largely, these commands highlighted here are largely memory management commands, so we're being able to allocate and reclaim them. We have two commands that allow to connect and disconnect. These commands are building that SPDM channel and IDE streams between the ASP and then the devices. And so we are generating the IDE keys, we're pushing them into the devices, and we're programming internal SoC configuration to allow that. So this is where we ask the device. So now we have this SPDM connection to the device, and we want to say, lock your configuration, don't change anymore, and we want to prepare the device to be attested to and to be used. So the TDI bind command takes both a device identity and a guest identity, and it connects those two inside of our SoC. It says, okay, now we know that this guest is bound to a TDI, and we transition the TDI to the locked state and then to the run state. This was the idea of moving straight through past locked was considered to be a simplifying assumption for the API. The run state basically prevents DMA and MMIO, which is redundant in our architecture. We can prevent that on the host side. So we transition to the run state for simplification. And then we have an unbind command. The unbind command does basically the opposite of what you'd expect. It's important to think about the unbind command also as the way to recover from errors. So if there's an error condition, either a device was ripped out of the box, or a device gets reset, or the guest falls on its face, there are a number of different error conditions that we need to handle. The unbind command is the way to escape those, and so we basically allow that to almost always succeed, so that we will just clean everything up. So attestation, which is a fun topic, we have three basic objects for attestation. We have the device's manufacturer certificate chain. We have an attestation report that's defined by SPDM and to a large degree by the device itself. And then we have an interface report, which is defined by the TDISP specification that describes the interface configuration, largely the MMIO ranges. We have some commands to retrieve those, and the hypervisor will retrieve them and hand them to the guest. And the guest will use this TDI info request to say, ASP, what was the last message that you retrieved? Give me the digest of it. So that way the guest can make sure that the hypervisor hasn't changed the objects in transit. So once the guest has done its authentication, and I kind of put a big asterisk there because there's a lot to be figured out with how to appropriately attest a device, the guest will then go through MMIO validation. So the guest has a range ID that it wants to write to map in, and it has a GPA. And it says to the ASP, I want you to validate this MMIO range. The ASP will then use its values that it knows about the interface and the MMIO ranges from the interface report, which contain the SPAs of the bars. It will do some lookups in our RMP table to figure out whether or not those pages were mapped to the guest, whether they were mapped appropriately to the GPA, and will ultimately confirm that the MMIO range is positioned in space on top of the bars in a way that the guest is expecting it to be set. And then once that's set up, once that's checked by the ASP, the SEV firmware will then write the RMP entry to an appropriate way for the guest to be able to access that memory in private address space. The SDTE write command writes this 512-bit SDT entry and for the interface, and this is where the guest is going to provide its guest paging mode, the pointers to its page tables. The ASP will provide some of the entries some of the values in that entry. This is where we bind the ACID value. So this is how we tell the IMMU this is the guest this device should access the memory with. And then once it sets the V bit, the validated bit for the SCTE, then the IMMU can start accessing memory for DMA for that device. When we have guest paging enabled, there will be a need to use the hardware accelerated VIMU. This is primarily necessary for a guest to have a trusted path to the IMMU so that it can invalidate IOTLBs and the IMMU TLB. So SEV-TIO, in conclusion, is intended to bring the devices into the trust boundary of guests. It also prevents traffic snooping and tampering using the IDE stream, and it can produce possible performance improvements by removing the bounce buffering requirement for access for DMA. If you want to learn more, we have information about in our white paper, and then there's also a technical preview of our ABI that you can find out what the specification for each of these commands are. And then this afternoon, we intend to have a BOF of some kind to answer some of the following questions, like what does the device model look like? Should devices change? Should they be enlightened for TDISP? How does the attestation flow work? Like who is processing the attestation reports? Is it the drivers? Is there remote attestation flows? Should we support all of that and provide all the hooks and flows necessary there? So with that, that's my talk. So are there any questions? Yeah.
So this relates to one of your earlier slides. I understand that IDE protects PCI traffic from snooping and tampering and stuff like that.
Mm-hmm.
But assume that DMA transfer is landing from the device in guest memory. Does some kind of re-encryption happen there? Because when the guest code is running, it will try to read the data that the device just produced.
That's right.
So is it integrated somehow into the memory controller? Because I figure that the encryption used for IDE might differ from the encryption you use for encrypting and decrypting guest memory.
Yeah, that's exactly right. Yeah. So when DMA comes through the IDE stream, it's encrypted at the device and decrypted at our root port, and then it flows to the IMMU, hits our data fabric, and goes out to our UMC, or our memory controller. And the memory controller, it's the same logic for SEV. You have keys, and it all gets tagged with the right guest's identification.
So it goes through that. From one of the earliest SEV specifications, I recall an expression calling it a high-performance EAS engine or something like that. So that I'm not sure if that's valid, if my memory serves right, but it goes through the same channel.
That's right. It goes through the same encryption engine that a guest would go through to access memory.
Thank you.
Yep. Sure.
It seems to me that if you're trusting, or you don't need to trust the device very far. What I think the best power out of this is the ability to say this device can DMA to just these specified areas because I've got VIO-MMU. And if it's a NIC, then you're using, you know, TLS or whatever. And
Nice. Yeah, so your point is, like, you know, we can use the IMMU to limit the GPA space that the device can actually touch. Is that right?
right, so you get rid of the bounce buffering, but you don't have to trust the device because there's many devices. If you're distrusting your cloud provider, it's probably the cloud provider's NIC in the first place and so on. So I think that it'd be better if you don't talk about it only as trust the device, but also as a way to improve device performance without having to trust it.
So you already have, before TIO, the ability to manage the space of memory that the device can touch through guest paging. But in that case, you know, we have the prevention of accessing shared memory. But at the same time, if you care about that, or you're in a conventional guest, then you can do that. We're not affecting that here. We're allowing that same control to exist here as well. So it's a sort of a layered approach on that security.
So when you have reached our state, is there any way to recover from that state? Your slide said not reconfigurable, but is it possible to reset the device and we go through attestation from within the guest or not?
You have to. So once the device enters the error state, TDISP requires the error state to, requires the TDI to go to the unlocked state, which is essentially the case where you have to go through that whole binding flow, you have to go through the attestation flow. So the recovery from that perspective is re-enumerating, rebinding, and re-attestation.
So my understanding is the PCI host bridge, you expect it to still be emulated, right?
Yes, that's true, right? So the like, you know, information about where the device lives in GPA space, like the MMIO ranges, all that's going to be provided by the hypervisor, and it's going to be untrusted. And that's why we go through the ASP to say, you know, the hypervisor told me this device lives at the GPA 5000 or whatever. Then can you confirm that for me? And that's what
Yeah,
the
I
ASP
got
is
that.
doing.
And so is there gonna be like a mix of trusted and untrusted devices, like on the same host bridge?
That's possible,
Emulated?
yes. Yes, that's possible.
Okay.
I have one question because I saw like in the TIO paper it said like, you know, the MMO mapping will not be accepted by the p-valid anymore. So the paper said it might accept through the GHCP core, I think. So I was wondering, like, you know, when you are going to destroy a VM, so who would release those RMP entries? Does the hypervisor need to do that, or like in the TIO unbanned, you know, the PSP firmware will release all of them?
So one of the commands is to do the MMIO validation. That's a command to the ASP, and that's going to get flowed through the GHCP protocol. That command is essentially p-validate, so you can both set and unset the validated bit for that MMIO range. And then, you know, the hypervisor can still reclaim pages forcibly, if it needed to, of all the MMIO ranges that have been assigned to that guest, just like it would for DRAM.
Okay, thanks.
Okay.
Okay, my question is, what is the scheme for firmware updates on the card? Is this bringing the card in error state then? You have to go through the loop, or is it forbidden to do firmware updates?
That's a great question.
Or do you rely on firmware certification and chain of trust?
Yeah, that's a great question. I mean, ultimately, what it broadens to, you know, how does a guest owner trust a device fundamentally? And a lot of that is device specific. There are bits in the TDISP spec that say, no, you can't update firmware while this TDI is in the run state. And so that can be a control to allow a guest to not have to worry about that. But if you do need to update firmware, and at the, you know, that would affect the guest, and it would be driven by the host updating that firmware. I think protocols need to be built in software to figure out what that looks like, and it may be device specific. That's a really interesting question to answer. Okay, I think that's it. Thank you guys.